So far we've been introduced to the linear momentum equation applicable for a control volume. Take a look at the terms. This is in general. This is for specific where you have particular inlets and outlets for the control volume. You can talk about the mass flow rate coming in, the mass flow rate going out, the average velocity in those ducts connecting or pipes connecting to the control volume. And then what was beta?
1.03.
It's a name of it, the name of beta. Linear momentum correction factor. That's right, linear momentum correction factor. For turbulent flow, it's not much greater than 1. Often this term is 0 because the linear momentum inside the control volume isn't changing with time. Maybe some flow in, some flow out, but it's not changing with time. And then these are the forces. And remember, always take a look at body force. Do I have gravity? Do I have weight? Is that important? I need to include it. Second one, any normal surface forces, any pressures. Are the pressure, on this side of the control volume high, that side low? And then also some shear forces. Some problems will have that viscous shear force at the boundary, and you need to consider that. So those three forces for the control volume, the body, and then two surface, normal and shear. And the normal comes from pressure, and the shear comes from viscous effects. Thrust is another concept, true? So if I have a control volume here, and I have just focus on this one outlet right here, the flow of the fluid is that way, going out of the control volume as shown, true? And if we take a look at our equation, let me go back and actually see about copying it. Maybe I can't easily. Maybe I can do a snipping tool, grab it like this, put over here, do a paste, edit, paste. So if we apply the linear momentum control volume analysis, this equation to this control volume, what do we find is we find that we have this outflow. We'll put the beta equal to 1, and it's equal to the mass flow rate times the average velocity. Now, we have to put this is a vector entity, and so if our coordinate system's like this, x and y, it's in the negative direction for that velocity. So I'm going to turn it from a general vector equation into just the x direction scalar equation. And so we see that it's 1 times m dot times negative v. Okay? Steady state, no, I'm not focusing on the ends, so just let those terms be 0. And now, if that was the only force acting on this control volume, nothing to restrain it, what do you think would happen with time with that control volume? It would move. It would move to the right. And so if it started to move to the right, then this term becomes non-zero, because it's picking up some speed as it moves to the right. It's accelerating toward the right. All right, so that would be non-zero. But what the idea is, sometimes you've heard of the term thrust. Thrust is a force, true? It's as if expelling this fluid out the back here, maybe of this nozzle, as I've shown it, generates an effective forward thrust onto the object that's expelling the fluid. What you would do is you would say, take this term and move it over to this side, When you moved it to that side, it would be just m dot v. And so now it looks like a forward thrust. Forward thrust being m dot v. Okay, trying to link in the use of this equation and how you would make it look like this expelling of the fluid from the control volume might look like a net force on a control volume propelling it forward, propelling it, making it move. So if there was no aerodynamic drag, nothing else, you know, this nozzle or this chunk would move to the right in the positive x direction, and it would look like there was some thrust force acting on it due to expelling the fluid out the back. The rocket burns fuel. It's burned at a particular rate. They give us the burn rate of 2 kilograms per second, and the combustion products are ejected with a particular velocity out the back of this rocket. Determine the thrust force acting on the rocket. Maybe I'll just put it horizontal, and we have the 1300 meters per second, m dot 2 kilograms per second. What is that thrust force? Is it really just product m dot v? Let's run it down. 2 kilograms per second, 1300 meters per second. What's a Newton? Kilogram meter per second squared. And sure enough, kilograms go, seconds squareds go, meters go, and we're left with the particular unit of 2600 newtons. Force thrust. A rocket car initially, the car initial combined mass of the rocket and the fuel is m naught. So m naught, if you want to start figuring out stuff, the initial mass of the car and the fuel. The mass of the fuel is consumed at a constant rate, and the rate of consumption is c. So c would be, you know, the change in the mass of the fuel with respect to time. And if I'm talking about a positive c, the mass of the fuel is leaving the car, so it's going out. All right, and it's expelled at a constant speed u, which is relative to the car or the rocket. So if the car is stationary, then this is going out at u, right? But if the car is moving at speed v, what is the speed crossing a stationary plane? I know that's issuing out the back of the nozzle relative to the movement of the cart with speed u, but it'll be coming across that plane by u minus v. Make sense? Okay. Neglect friction and aerodynamic drag resistance. The rocket starts at rest, and you have some amount of fuel, m sub f. It's going to be consumed at a constant rate c. Predict the time that the fuel runs out, and then predict the velocity of the car at that time that the fuel runs out, which will be the maximum prediction of the maximum speed. Okay? That all makes sense? Okay. So we can use the concepts in fluid dynamics to introduce a control volume. Now, what's going to be happening inside this control volume is that the cart's going to be speeding up. The cart's going to be inside the control volume. So V is going to be changing with time. Also, the mass is going to be changing with time too, because the cart made up of the mass of the cart and the mass of the fuel, and the fuel's going away as it's being accelerated. All right. And then what do we have? We have no ins, but we have an out. We have an out, which is acting like a thrust force. We'll leave it like this, m dot v on the out. Right. And then over here we'll say, okay, any forces acting on our control volume? Well, we have no resistance, no aerodynamic drag, and we could treat the expelling of the fluid out the back as a thrust force, or we could just leave it over on the right-hand side. We'll leave it over on the right-hand side right there. Okay. So it takes a little bit to think about it. You want a control volume like this. Make it big. Why? Because this cart's going to be moving with time, moving over here, then moving over here. Okay, it's going to be moving within the control volume. And I like to think about a fixed control volume. You can do it a different way. You can have an accelerating control volume, but this way will work in the analysis. And so for that fixed control volume, there's no forces acting on that control volume. We do have the time rate of change of the mass and the speed of the cart. We're going to use V. We'll use V for the speed of the cart. And if you want to plot it, you think about V as a function of time. It starts at 0, and it's going to rapidly increase and then taper off because the fuel is going to be expelled and be done, right? Actually, it may do something like this. Maybe, yeah, something like that, where it's going to reach a maximum speed and then just coast. All right. So that's what this is V. All right, but the mass right here, what is that? That mass is the mass of the cart and the fuel that make up the rocket car. So what is the mass doing? It's made up of the constant cart plus the mass of the fuel. All right. So what is the plot of the mass as a function of time doing? It starts out at some initial m0. They give us m0, and it's going to finally go down to mc, the mass only of the cart without any fuel, and the burn rate is linear until it hits it. And the slope of this line is negative c, the rate at which c is right here. The mass of the fuel in the rocket is decreasing with time. Okay. So we could expand this term right here. We could put the mass of the cart plus the mass of the fuel, which is a negative c times t, v. There's a lot of work in that. I'm trying not to take too much space on the board, but can you see that what you have, this equation works for time t going from 0 initial to when the fuel runs out. It doesn't work after the fuel runs out. So it's mass of the cart minus c t. T. Do you follow that or not? All right. Is this time derivative on both of those terms? Is it the product of the mass times the speed? True. Is the mass of the cart constant with respect to time? Yes. Is the constant c a constant with respect to time? C. Is t time a function of time? Yeah, so don't forget that you're going to differentiate that, right? So t is right there. And what about this v? Is this v a function of time? It is, and you can think of it like this. It starts at 0 and it's going to go. Okay? There may be a kink in this. I'm looking at the equation. It may go like this and then just stop when the fuel stops. It may do something like that. Or it may have some curvature because it's going to have some curvature because what's happening as it's going is it's less mass, and so it's easier to accelerate. So maybe it goes like this and then stops, right? It's heavier, speeds up, runs out of fuel abruptly, and it stops, and now it's at that same speed. It's not accelerating anymore, right? Maybe I should have asked you to figure that out, huh? Plot, v is a function of t. Which one is it? Does it have it belly up, or straight line, or belly over? That's a hard question, but what's happening is it's heavy and it's lighter. Okay, now let's take a look at this term right here. This term, we have a beta, we'll put 1. And then we have the mass flow rate. This is mass flow rate that's exiting. And is that the C? Is C the, it's a positive constant C, which is our rate at which the fuel is being consumed, and that's the rate at which it's exiting. True? And what about V? Well, it's a vector entity, so we have to make sure and account for the sign when we go to a 1D scalar equation in X. And we see that it's being expelled in the what direction? Negative direction. And what speed is it being expelled at that's crossing the control volume surface? The cart's nozzle's moving with time, and so it's leaving at u minus v. This is u is the constant speed at which it's exiting relative to the nozzle, but it needs to leave the control volume, and the cart's moving at constant at a changing speed, lowercase v. So that's the speed at which it leaves the control volume. That's the hardest thing to do right there, right? To get that equation, to apply it to this problem. I pause. I let you think about this. Are you comfortable with it? What would you change? Well, we're trying to apply the control volume, and I don't want an accelerating control volume, but I want the stuff inside the control volume to accelerate. Okay? But I have fluid leaving the backside of something that's in the control volume that's accelerating, that's speeding up. And I really need the speed of the fluid leaving the non-accelerating control volume. So it's V, it's U minus V. So this is our differential equation, ordinary differential equation. Our initial condition is V at time 0 is equal to 0. It starts at rest. So you look to separate and integrate. So how do we do this? So let's go ahead and first of all put one on the right side, one on the left side. Derivative with respect to time of the mass of the cart minus CT times V of the cart is equal to C times U. Now the next one, differentiate this with respect to time. What does that give us? Does it give us M sub C minus CT times dV dt plus negative C times V? So I said if I need to differentiate f of x times g of x, in general, that's the derivative of f with respect to x times g plus the derivative of g with respect to x times f. True or false? And what was that called? Product rule. Product rule. Yeah. There you go. Chain rule, product rule. All right. So at this point, what do? We look over here. We have Cu minus Cv. Can we cancel those on both sides of the equation? Simplifies it. All right. Now we're left with something that I want to now separate. I want, what is my independent variable? Time, lowercase t. What's my dependent variable? Speed of the cart, rocket car, whatever I'm calling it. That's lowercase v, true? So maybe I come in here and I say, there's v. Is there any place else where there's a v? I'm so thankful those just canceled. Otherwise, it'd be a nastier problem. That's just the only place v is true. But where is t? There. In there. Is that it? Is c a constant? Yes. Is u a constant? Yes. So what are we left with? We can separate. We put dv is equal to c u dt divided by m sub c minus ct. Did I separate okay? Next step in solution, after you separate, you integrate. You can put the limits to work so you can avoid the constant of integration, but we'll integrate from time 0 to some future time t, and the speed at 0 is 0 to some unknown future time t. This equation only works until the fuel runs out. As soon as the fuel runs out, then that equation doesn't work anymore. Doesn't go off to infinity. And so this is equal to v as a function of t is equal to, you do the rest. What is that? Oh boy. What is the integral of that equation? Natural log. C and u are a constant. The only place t is right there, t. So you pick up a constant, or you pick up a natural log, and so it looks like a, let me do it this way, u natural log m naught divided by m naught minus ct. Messed up. This is always m naught. The mass of the starts the initial mass, and then you take off the fuel as it burns. This is all m naught. Sorry about that. M naught, m naught, m naught, m naught. The equation for the mass is m naught minus ct. And that's what we put right in here. Okay. So there's the solution. It's nasty. When does the fuel run out? Do we even answer that time? T is equal to mass of the fuel divided by C. Isn't that when it runs out? The mass of the fuel initially is mf, and C is the rate at which it's consumed. So that's when it runs out. Maybe I put OUT on the subscript, T out. And now what is the maximum velocity of the car? Starts from rest. I put in this equation, V max equal to U natural log initial mass minus C T out. I didn't give any numbers, so you can't convert like kilograms and meters per second. That's the maximum. Did that work for you? Is it good? Ready to move on? Did we solve this problem? I don't think so. Do you remember this problem? Stop me if I did. I can't remember if I solved it in AM.
Yeah, we did this one.
We did?
Yeah.
Okay. So this is, you have to hold that in place. All right. Linear momentum correction factor, that's that term beta. Did I derive the analytic expression for it last time? So let's go ahead and do that. So we have flow. I'm going to just say it's in a pipe, but anything with a cross section. But a pipe is easy to discuss, and it follows what we did for the average speed in a pipe. And you look down the pipe, and you have the center line looking like the middle, and you introduce a coordinate system and a ring. So let's talk about a ring of fluid that's at distance r, lowercase r from the middle, and lowercase r goes from 0 to cap r, the overall radius of the pipe. And everywhere in that red ring, you have the same speed. True? You have some speed like this, which is the same everywhere in that little dA in that red ring. That red ring has a little area dA, which is 2 pi r dr, and it has the same speed. If the red ring gets larger, it is a lower speed. If the red ring is smaller in radius, it's a faster speed because it's near the core or the center line of the pipe. And what we'd like to do is we'd like to have a very easy equation from linear momentum flow rate. We would like to take the mass flow rate times the average speed in the pipe and make that equal to the linear momentum flow rate. Well, it's not precisely equal to the linear momentum flow rate. We add a correction factor, beta, on the left-hand side. And on the right-hand side, we'll calculate the linear momentum flow rate very accurately using integration. So we'll sum all of the V's of the little chunk of fluid traveling at that speed, dm dot, and that will give us the linear momentum flow rate. So this is the speed of each ring times rho v of that ring dA of that ring, where this was dm dot. It's the mass flow rate in that red ring, which is the product of rho v of the ring and the area of the ring. And so if we sum up over the mass flow rates, or if we sum up over the areas, we'll get the correct linear momentum flow rate through that cross section. So at this point, we're looking for beta, and we replace the mass flow rate as rho, the area, V average, and we had V average there. So we find that our equation for beta is equal to the integral, and we'll bring the V, we'll put one of the V averages across, bring it across. The rows will cancel. V, put another V average over there. And then we'll have dA and 1 over area. And that's the equation that we had in the textbook, something like 1 over area, the integral of V over V average squared dA. All right. For turbulent flow, often just a little above 1. We'll calculate a few of them now. Okay, let's go ahead and calculate them. That look good for a derivation? All right. So here's a velocity profile, and it's for representing a turbulent flow velocity profile in a pipe. So if I again sketch the profile, there's R going out that way from 0 to cap R. And it would go 0 here and 0 here. And it would be maximum in the middle and go steep at the edges. That's what this equation right here gives us. U as a function of R is the maximum times 1 minus lowercase r over cap R to the 1/7 power. Now for this velocity profile, do 3 integrations. Get the average speed U average. Okay, so we just recall V average was equal to 1 over A, the integral of V dA. That's our general equation for the average speed. So we'll substitute 1 over the area, the integral of U max times 1 minus lowercase r over cap R to the 1/7 power dA. All right. And we'll go ahead and say it's a round pipe, and so I can replace the area is pi r squared for that area. And we have U max, and we have 1 minus lowercase r over cap R to the 1/7 power. This dA we can replace by 2 pi r 2 pi r dr. Did that make sense so far? So cancel the pi's. Bring this cap R squared here inside. Put one of them right there and put the other one right there. So now we have a new variable of integration. It's lowercase r over cap R. So a new variable of integration, I'll call it x, is defined as lowercase r over cap R. And lowercase r used to run from 0 to cap R. And our new variable of integration runs from 0 to 1. 0 to 1. And so what we find is the equation for U average or V average. I guess I'm a little inconsistent using U and V, but since one-dimensional, usually switch it. So here's U AVG is equal to U max times the integral from x equal to 0 to x equal to 1. 1 minus x to the 1/7 power 2 times x dx. You follow? Now, how would you do that integral if you had to do that integral? I know it depends on the context. Do I have to do it with what resources? You know, I'll say any resource you would like. Yeah, that's what I'm going to show you, of course. So what you would do is, it seems like a lot of students already know about Wolfram Alpha online. Oh yeah? How do you guys know about it? I know when I first started teaching and it came up that it was available, I would show students, they'd be like, wow, this is neat. But I guess it's out and the people know about this useful tool. So just find it, wolframalpha.com. Okay? And you can sit into this box right here and type something like integrate. And it's 2x. You don't have to put the asterisk for multiplication if you don't want. You can. 1 minus all to the power 1/7 from 0 to 1. And it understands what you're trying to do. And it coughs back and it says, I think you're trying to do this. You're trying to compute a definite integral, 0 to 1, 2x, and then they put the x to the 7th. 1 minus x dx. Yeah, that's what I'm trying to do. And here's your answer, 49/60th, which is around 82. So the answer is around 82%. So if we go back, what we see is for this velocity profile, U average is about 82%, 49/60ths of U maximum. All right? So we were able to complete this integral using the online Wolfram Alpha. And so we were able to answer part A. The average speed U average is 82% or 49/60ths of U max. Now, what about the next one? The kinetic energy correction factor alpha. Okay, let's, and then the linear momentum correction factor beta. Let me insert a new page. Which one do you want to do first, alpha or beta? Alpha? So alpha was, I forgot the name of it already. Alpha was, what is it? Alpha? Kinetic energy correction factor. We derived the equation for it last time. Was the equation something like 1 over the area, the integral of V over V average, or U, let me use U, U over U average to the third power dA. Was that alpha? Somebody want to help me with that? Is that true? How about I pause and then, oh, you already have it on your equation sheet? He's looking at his equation sheet. What equation is it in the textbook?
It doesn't say.
Oh, it doesn't say. I thought I put equation numbers by the...
No, that's the only one that doesn't have it.
Oh, the only one that doesn't? Okay, well. So there you go. Now, so what we do is we say it's 1 over pi r squared for the area. The integral of the V over V average. Well, V was U max times 1 minus lowercase r over cap R, all to the 1/7 power. And V average we just computed was 49/60ths of U max. True? And that's all cubed. And then we have 2 pi r dr. Make sense? We're not going to be able to fit beta in that page. We'll just do alpha this page. And so what about the pi's? They cancel. Take this r squared right here, put it over here, put it over there. Cancel this U max. So what we end up doing is an integral of 60 divided by 49 times 1 minus lowercase r over cap R to the 1/7 power, all of that cubed times r over cap R. Ooh, I forgot a 2. Times 2 times r over cap R, derivative of r over cap R. So we do the integral from 0 to 1, 2 times 60 over 49, 1 minus x to the 1/7 to the third times x dx. That's what alpha is. I sure don't want to do that by hand, do you? And so we're thankful that Wolfram Alpha exists. And if you do beta, I think I can just figure it in. Here's beta. 1 over area, the integral of U over U average squared dA. True? So if you would reproduce the same steps, but beta is equal to the integral from 0 to 1 of 2 times 64 divided by 49, 1 minus x to the 1/7, all of that squared x dx.
60 instead of 64.
Oh, yeah, 60. 60 instead of 64, thank you. Does that look good? And so you would type it in. This time, if you notice, I typed it in with an asterisk for a multiple sign, multiplication. I like it. You know, sometimes when you're coding in Fortran or C or whatever, syntax, one little oops, and you're done, right? It's toast. It won't work. Well, here it seems to be a little more flexible, which is a little more user-friendly. And I said, this time I put a dx in. I don't think I did last time, did I? Is there a dx in this? So it understood, okay, you have the variable x, and yeah, you're doing x. I understand dx, right? So that syntax is a little more flexible. And that's the cube on that long expression with 60 over 49 and 2 on the outside. And so anyway, here is alpha. It's around 105, 1.05, 5% larger. And then there's beta. And I like it. They show you, okay, it looks like you're trying to compute a definite integral. You can check your work. Yes, that's right. If you want to, it looks like it was able to do it without numerically, you know, doing it by figuring out what rules to apply and then putting in the numbers, and it gets a ratio of numbers. Or if you just want the numeric value, 1.05. In here, it's around 1.02 for beta. It's very close to 1, so often neglected if it's turbulent flow. All right, let's solve this one, right? So we have 8 centimeter diameter water hoses connected. So initial diameter water hose connected to a 2 centimeter diameter nozzle, so it necks down like this. So this is state 1. State 2, the diameter of 2 is 2 centimeters. The diameter of 1 is 8 centimeters. And the water shoots out horizontally. The mass flow rate is 38 kilograms per second. Determine the force needed to hold the nozzle stationary. So it's like we have handles on this water nozzle. And we have to first, it's nice if we know what direction we're going to have to hold the water nozzle. So do we push forward on the water nozzle handles to hold it stationary, or do we pull back? Push forward. So we'll put that as our force in the positive F direction, needing to keep the nozzle stationary. So the first thing to do is to introduce a control volume. The control volume will go like this, cuts through the surface of the pipe through the water, comes to the front, cuts through, and then has the force acting on the control volume at the handle of the nozzle. So for that control volume, we can do a linear momentum analysis. So what does the equation look like? We have the sum of the forces acting on the control volume. The force of the handle, true? Is there any other force acting? Well, you have fluid pressure right there. So there's P1. And you had fluid pressure right there, P2. But P2 is ejected to the atmospheric pressure. So it's 0 gauge. But what about P1? So F is in the positive X direction. P1A is in the positive X direction. Okay, so we want to be able to calculate P1. Let's continue to write the linear momentum equation. Steady state, so that term is 0. It's no acceleration with time. and we're going to have plus the beta to m dot v exiting, that's out, minus beta m dot v in. There's our outs and there's in, one out, one in. We take a look at this v is in the positive x direction. So this is our x direction. So F was in the positive x direction. The pressure 1 is in the positive x direction. V out is in the positive x direction. And the mass flow rate, so what we have is we have the beta will approximate as 1. So it's just mass flow rate B2. Then we have minus this V right here. This is V1 coming in. And that's in the positive x direction. So we'll pick up minus m dot v1. M dot 1 is equal to m dot 2, so I don't have a subscript on the m dots. So at this point, what we want to do is we want to find F. So do this. There's our equation for F, the force to hold it. We have to take a look at all the terms. I'm going to put a check mark on top of the ones we know. Do we know m dot? 38 kilograms per second. Can I get the area 1? That's pi d squared over 4. I'm going to have to work to get P1. How about V1 and V2? I'll have to work to get those velocities as well. So let's just do some work on the side. What is V1? Is it the mass flow rate divided by rho A1? And then we substitute numbers, 38 kilograms per second, 1,000 kilograms per meter cubed. The diameter 1.08 meters squared pi d squared over 4. And then we get a value for V1, true? And what did we calculate for V1? Can you verify that we got some number like 7.5598 meters per second? Too many digits, but your calculator can keep them all, so let's keep them all. If you have a calculator, can you use it? Agree? Now the other one, you can do it a couple ways. You can do it this way. You can say mass flow rate 1 is equal to mass flow rate 2. It's pi, rho, it's rho times A1, pi D1 squared over 4 times V1, rho pi D2 squared over 4 times V2. Cancel these terms. And what we're left with is that V2 is equal to V1 times D1 over D2 squared. And so the velocity at the exit is the velocity at the inlet times the diameter at the inlet, 8, divided by the diameter at the outlet, 2. That ratio is 4. 8 over 2 squared, so it's 16B1. It's going to come out 16 times faster. Is that true? Do you like that? So we can combine these terms right here, minus P1A1. We have plus m dot. V2 is 16 times V1, so we're going to have 16 minus 1 times V1. You can combine it like that, right? Okay. So we really worked quite a bit on this term, but I need P1. So can somebody calculate P1 for me? All right, so we use the Bernoulli equation to go along a streamline from state 1 to state 2. Okay, and that Bernoulli equation had, I'll try and tuck it somewhere. Where should I tuck it? Put it right in here. How's that for use of word space? So it's a P1 plus 1/2 rho V1 squared equal to P2 plus 1/2 rho V2 squared. No changes in elevation, so there's no rho GZ. And this is 0, or atmospheric, or gauge 0. So we calculate that P1 is equal to 1/2 rho V2 squared minus V1 squared. We notice that V2 is 16 times V1, so it's 1/2 rho 16 squared minus 1 V1 squared, right? And so you could almost forget the minus 1. 16 squared is like 256. Minus 1, 255, blah, blah, blah. So when you substitute numbers, you get 7.286 Pascal, kilopascal, megapascal, what? Pascal. I'd like to put a kilo there. Put a 7 point. Do you agree? I only see a few head nods and a few thumbs up. Do you agree? All right. So that's P1. Multiply P1 by the area, and you'll find out what this pressure term is, and then also calculate this effective force. So we want to sum up. I want to know what this is plus that for the force. Can you do that for me? All right, so we calculate that pressure to be 7.286 kilopascal, true? Now we multiply by the area, which is pi d squared over 4. If you multiply by the area, pressure 1 times area 1, what do we pick up for that force? 30 what? 36,532 newtons. So 36,000. It's in a negative direction. Okay. Now let's jump over here. What is m dot times 15 V1? Did you calculate that? 4308. Is that it? And that's newtons or kilonewtons? Newtons. So both of these are newtons. So let's add them up, and what do you get? What do you get?
I'm still confused in the last part. I'm still ending up with 7.286 kPa. I'm just working through the units.
Right. So let's go ahead and do this. It's 1,000 kilogram per meter cubed. This was meters squared per second squared. So a kilogram meter per second squared gives us a newton. That one leftover meter goes to meter squared. So without the 1,000, you're left with a newton per meter squared, which is a pascal. So this pressure is 1,000 times 1/2 255 7 point, oh I forgot the number, 5596 squared. So 7.5596 quantity squared. So this is 7,286. You still have 1,000 multiplying right here. Did that help?
Yes.
No. So this is the correct answer in kilopascal for that pressure, high pressure. And so what do we get for the force needed to hold it? It's not positive, is it? So we have negative 32,224 newtons. And so what does that tell us? You're having to pull it back instead of push it forward? Let's solve this problem. A fan with 61 centimeter diameter blades moves so many cubic meters per minute of air. The air is at 21 degrees C and 100 kPa. Determine the force needed to hold the fan in place and the minimum power for the fan. So we think about large fan blade with a motor connected to it. That's really a poor looking. Let's try it again. Large fan blade with the motor connected to it. And it issues a relatively uniform velocity profile. It's not perfectly velocity profile, it's not perfect uniform, but on the outlet of the fan, it's a uniform velocity profile. All right. And we know that the diameter is 61 centimeters or 0.61 meters. And we know the volumetric flow rate, AV, is equal to 56.6 cubic meters per minute. So we could calculate what is this V average coming off the blade, this V average right here, right? And so that's going to be the AV divided by the A, 56.6 meters cubed per 60 seconds. The area is pi, diameter 0.61 meters squared, divided by 4. And I'll pause and make sure you catch up to that, and let's just... So the velocity is 3.228 meters per second. All right. Now, a fan draws in relatively quiescent air, non-moving air, and makes it move. That's what a fan does. So we want to draw a control volume that helps reflect that. So our control volume will be right across the outlet of the fan, and then it'll be sweeping back on the back side of the fan, a big, large, sweeping control volume like that, because the fan is drawing in air all along a large area, but it's throwing it out straight ahead. Make sense? So for that control volume, what we want to do is we want to do a momentum analysis, linear momentum analysis, to determine what is the force that's acting on the air, the net force that the fan exerts on that control volume, the air. Likewise, then the reciprocal is what the force pushing back on the fan, the effect of on the fan is, right? Equal and opposite forces. Okay. So what is F? So we do the x direction linear momentum equation. We have F in the positive x direction. It's equal to steady state, and then we have the inflow, but the inflow has negligible momentum coming in. Does that make sense? Because it's all coming in very quiescent, large area on the in. And the exit, what about the exit? It's all coming out over a concentrated area going out. Okay? So what we have is it's equal to the beta, which is 1 for this problem, the exit speed, V, and then the mass flow rate of the air. And it's exiting in the positive x direction. So there's negligible input, and it all exits with that momentum, the momentum flow rate. So get rid of the beta. Beta is 1. So if I want to know force, I know the V already. I just need to get the mass flow rate. How do I calculate the mass flow rate? Rho AV. So what is rho? It's going to be the pressure, molar mass of air, ideal gas constant, absolute temperature. They gave us 100 kilopascal. That's our absolute pressure. 21 degrees C. We have to add 273 to get to be 294 Kelvin. And so you calculate the mass density of air in the side to be about 1.185 kilograms per cubic meter. So then you can calculate the mass flow rate to be 1.118 kilograms per second. And then stick that in there, and then we calculate the force to be around 3.61 newtons. So that's the force needed to hold the fan. Which direction is it acting? It's pushing forward. It's pushing forward because the fan is going to be pushing back on the support structure. Make sense? All right. Yes, sir. Rho is equal to PM over RT. Yeah, you need to know that. A lot of people are tattooing silly things on their body. If you want to tattoo, you know, the ideal gas law, I won't make you cover it up. Okay? May not be the smartest thing to tattoo on your body, but hey. I be an engineer and then misspell it. Oh, man. I misspelled engineer. So now it's tattooed. Now, what's the minimum fan power? The minimum fan power. Well, it kind of Bernoulli's equation, that's all it is. And if you remember, we had an energy concept. Pressure was energy per unit volume. We had a, what else did we have? What else do we have? We had energy per unit mass. We had energy per unit weight, which was head. Right? So all those concepts can help you juggle. But what do we have? How am I going to calculate that power? You can do the head idea. So you can do it this way if you want. Do some streamline that goes from this point all the way back to that point. So 1 to 2. Okay. And it goes through the fan. And so when it goes through the fan adds some energy to it. Okay. We can put it in terms of pressure, energy per unit mass, or energy per unit weight. Either form of those modified Bernoulli's equations will work. Which one do you want to work on, or work with, or play with, or something? It's going to be pressure. Do you want to use pressure, energy per unit mass, energy per unit weight? Energy per unit weight. So it's going to be P1 divided by rho g plus would have V1 squared divided by G plus H1 or Z1, well, H1 is fine, you know that's elevation, plus the head introduced or gained by the fan, because the streamline goes through the fan, and so that's a gain, that's a modified Bernoulli, is equal to P2 divided by rho G plus 1/2 V2 squared divided by G plus H or Z2. There's a modified Bernoulli. Okay. A lot of these terms are zero. So what about P1 and P2? The fan is really to motivate to speed it up. It doesn't change the pressure. Okay? So the pressure change is zero. Okay. Now, what about the kinetic energy on the inlet? We said it's quiescent air being drawn far away into the fan, so V1 is zero. Kinetic energy at 1 is zero. There's no real information about head change, so just like the pressure change. So what does this all boil down to? It makes it move. The head gain by the fan is realized by an increase in the kinetic energy of the fluid coming out, the air. So the head gain by the fan is equal to 1/2 V exit squared divided by G. Now when you compute that, you should get units, SI units like meter. It doesn't make much sense in the sense, but it's energy per unit weight. If you, this is energy per unit weight, I would want to multiply by the weight flow rate, which is, I know I'm kind of bouncing here, but the weight flow rate is the G times the mass flow rate. Instead of talking kilograms per second of mass flow, I'll talk newtons per second of weight flow. So if I multiply the fan head times G m dot, I will get the W dot fan. I'll get the fan power, the power, minimum power needed to be supplied to the fan in the form of electric energy, assuming all that electric energy is converted into the fluid flow energy. So that's why it's minimum. If your fan has any losses, friction, electric motor losses, then that electric power is going to be higher. Okay, so it's going to be 1/2 the velocity squared over G times G, those cancel, times the m dot. All right, 1/2 the velocity, 3.228 meters per second squared, times the mass flow rate, 1.118 kilograms per second. Look at our units. A newton is a kilogram meter per second squared. That'll give us a newton per second. Well, I need a newton times a meter, then that's a joule, and it's a watt. So this turns out the power to drive the fan, the minimum power is about 5.83 watts. Make sense?